Hello and welcome to the Blackboard. If you are here, it is because you have already seen the training module of AASHTO T27 and ASTM C136 presented by Tech Training LLC and still have further questions. So hopefully we can answer those questions here. So let's go ahead and get started. In this session of the Blackboard, we're going to be performing a sieve analysis on coarse aggregate. In the training program, we did a sieve analysis on fine aggregate. So here we're going to do coarse aggregate because coarse aggregate can be slightly trickier, but it is performed the exact same way as it is for a fine aggregate sieve analysis. So let's go ahead and get started. So some of the things that we're going to review here are going to be checking that not more than 0.5% by mass of total sample weight passes any given sieve after 1 minute of hand sieving. We'll explain what that is. We're also going to ensure that the sample after sieving is within 0.3% of the original sample weight. We're also going to calculate the individual cumulative percent and percent passing of each sieve. And then finally, we're going to calculate the fineness modulus of a coarse material. So let's assume that we have done our sieve analysis. We started with an 11.5 pound sample, and we are running this sieve analysis to compare it to ASTM C33 size number 56. We'll talk about that specification in a moment. However, we have completed our sieve analysis and we have recorded the following masses on each individual sieve. As you can see, those numbers are listed here. But before we do any calculations, we want to ensure that we have actually sieved this material for a sufficient amount of time. We do this by checking that not more than 0.5% by mass of the total sample weight passes any given sieve after 1 minute of hand sieving. So we do this by selecting a sieve and putting it snugly into the pan and then tapping the sides of those sieves about 150 times per minute, turning the sieves about 1/6 of a turn every 25 taps. Now for this example, let's just assume for a moment that 0.09 pounds of material passed through that sieve after 1 minute of hand agitation. We would take the 0.09 pounds divided by the original sample weight, 11.5 pounds, and multiply this value by 100. This would be 0.8%, which is greater than the specified 0.5%, meaning that we have not sieved this material for a sufficient amount of time and therefore must re-sieve it and increase the amount of time that we sieve the actual material. However, for the purpose of this example, let's assume that we did actually sieve long enough and move on to our next calculation. The next quick quality check that we can perform is to ensure that the sample after sieving is within 0.3% of the original sample weight. We do this because if we lose more than 0.3% of our representative sample, it is difficult to say with certainty that after agitation, our sample is still representative of the supply. Now, if we've gained more than 0.3%, it is most likely due to the fact that our sieves were not particularly clean when we started the test, meaning that we have picked up some material from a previous test. So our sample after sieving should be between 99.7% and 100.3% of the original sample weight. However, in this example, we started with 11.5 pound sample, and after sieving, we checked the masses on each sieve, and we still have 11.5 pounds of material. Therefore, in this case, we came in at 100%, obviously in between the 99.7 and 100.3, and therefore we're going to continue with the procedure. So we can now proceed with our percentage calculations. Now on the 1.5 inch sieve we had no material, so clearly that's 0% retained. However, on the 1 inch sieve we had 0.7 pounds of material. So here what we want to do is take the 0.7 pounds and divide it by the original sample weight, 11.5 pounds, and multiply this number by 100. So the individual percent retained on the 1-inch sieve is 6.1%. Now on the 3/4-inch sieve, we see that we have 4.6 pounds of material retained. So same procedure. We're going to take the 4.6 pounds, divide it by the original sample weight, 11.5 pounds, multiply this number by 100, and 40% of our sample was retained on the 3/4-inch sieve. For the 1/2-inch sieve, we're going to take the 2.8 pounds, divide it by the 11.5 pounds, multiply this number by 100, and we see that 24.3% of our material is on the 1/2-inch sieve. So I think that you can see how this works now. So we're going to fill in the rest of the numbers below and move on to cumulative percent retained. Now to get the cumulative percent retained of any sieve, all we do is take the individual percent retained of that sieve and add to it the individual percent retained of all the previous sieves. Therefore, if we start on the 3/4-inch sieve, we see that we have 40% individual percent retained. This, combined with the 6.1%, which is on the 1-inch sieve, gives us 46.1% cumulative percent retained on the 3/4-inch sieve. Now if we move to the 1/2-inch sieve, we see that we have 24.3% individual percent retained. This, combined with the 40% on the 3/4 and the 6.1% on the 1-inch sieve, gives us 70.4% cumulative percent retained on the 1/2-inch sieve. And I think you can see how this works. So let's fill in the rest of the numbers below and move on to percent passing. To calculate percent passing, all we do is subtract the cumulative percent retained from 100. As an example, on the 1.5-inch sieve, we have 0% cumulative retained. Therefore, 100% of our sample must have passed through that sieve. On the 1-inch sieve, we have 6.1 cumulative percent retained. Therefore, 93.9% of the sample must have passed through that sieve. On the 3/4-inch sieve, we have 46.1% cumulatively retained. Therefore, 53.9% must have passed that sieve. And we're going to go ahead and fill in the rest of these values below. Now that we've calculated our percentages, let's compare our results to a specification. ASTM C33 is the standard specification for concrete aggregates. We're going to take a look at our numbers compared to a coarse aggregate size number 56. The grading requirements of a size number 56 state that 100% of the sample must pass through a 1.5-inch sieve. As you can see, this sample has. For the 1-inch sieve, it states that not less than 90% can pass through the 1-inch sieve. We have 93.9% of the sample passing, therefore this requirement has also been met. On the 3/4-inch sieve, the minimum allowable passing is 40%, while the maximum is 85%. This sample has 53.9%, again meeting the grading requirements of a size number 56. And as you can see, this sample has met all of the grading requirements for ASTM C33, size number 56. Let's now calculate the fineness modulus of our sample. We do this by adding the cumulative percentages of all the standard sieves coarser than the 150 micron and dividing this value by 100. The standard sieves include the 6-inch, 3-inch, 1.5-inch, 3/4-inch, 3/8 inch, and then the number 4, 8, 16, 30, 50, and 100. Now listed here are the cumulative percentages of our material. And as you can see, all the sieves we used were coarser than the 150 micron or number 100 sieve. However, we cannot simply add up these cumulative percentages and divide by 100, as we would get an erroneous fineness modulus. Let's recall for a moment the standard sieves that we're going to be using to calculate our fineness modulus. So when we do our calculation, we're not going to include the 1-inch sieve or the 1/2-inch sieve, as these sieves are not part of the standard sieve series. Furthermore, we have to include the 8, 16, 30, 50, and 100 sieve in our calculation. And when we add these standard sieves into our calculation, we get a total of 733.9 for a fineness modulus of 7.34, rounding to the nearest 0.01. And this will conclude this Blackboard session on sieve analysis calculations. As always, we hope this helped. Thank you.